Welcome to Aerodynamics class number 138, and today we're finishing this podcast series over ground effect, and not just regular ground effect, but airfoils going over a wavy surface. So, for example, waves in an ocean. And in podcast 137, we went through the first half of this series. In this podcast, we're going to go through the second half. And we are going to look at the same paper again, finish off this paper called Airfoil Aerodynamics in Proximity to Ground Effect for a Wide Range of Angles of Attack. And you can find this in the link in the description. It's open access, so you can play along at home if you like, or if you're watching this if you're listening to this on Spotify, you can watch this on Spotify and or YouTube. And on YouTube, we have some other goodies as well. So in the last podcast, we looked at the overall effects of the wavy surface on lift, drag, and moment coefficients. So let's just quickly go through the setup again, just to remind ourselves of what it looks like. We had a NACA 4412 airfoil, which is a very common airfoil. Like that's the one that's usually used the most as a general approximation, or at least a first approximation for most aircraft wings. And we have a CFD setup here where we have the airfoil in a very big domain. That's very nice. It's quite a far away distance from the inlet, outlet, and the top. Then we have the ground is a wavy, like a sinusoidal pattern here. And they made this wave ground move along with time so that this airfoil will be over a different part of the wave with preceding time. So it might go over a trough, then a peak, and then continually go over trough, peak, etc., like that. And the CFD was fairly well validated, and we found that in the last podcast that, as expected, the waviness does affect the lift, drag, and moment coefficients with time. So, for example, if you're over a peak, typically the lift coefficient is increased, the drag coefficient is reduced, and the moment coefficient is reduced as well. Whereas for over a trough, the opposite is true. And as we increase the angle of attack, this waviness is still there. So, for example, at 2 degrees, there is a significant waviness. So, like whether you're over a peak or trough, the lift will be significantly altered. Whereas when you're at an 18-degree angle of attack, this is also the case. So, in other words, the lift coefficient, for example, fluctuated with times and producing peaks and troughs corresponding to the peaks and troughs of the wave. Now, in this podcast, let's look further into what's happening here, and in particular the details. So we're going to be looking through like the relative changes, as well as some flow physics, as well as some different ride heights, and we'll see some somewhat unexpected results. So in figure 7, which is this one here, for those of you watching this, we are given the absolute changes and the relative changes in the lift, drag, and moment coefficients for each angle of attack. It's not just the absolute, but the relative ones in a percentage. And the relative ones are the changes. So they got the maximum and minimum lift coefficient, for example. They then divided that by the average, and they found what that fluctuation was. So interestingly, while the absolute fluctuations in the lift coefficient increase as angle of attack increases, so you can see here it increases quite nicely, the relative changes remained fairly consistent with the change angle of attack. So the fluctuations hovered around 15 to 20% for the entire angle of attack range. What this means is that, so for example, you have the NACA 4412 airfoil, let's say it's at 4 degrees, and it's producing a lift coefficient of, 0.5. And then you put it over the wavy surface, and it might boost it to maybe 0.6, let's say. Then when you increase the angle of attack to 15 degrees, you get that exact same percentage change again. So even though the absolute value increases, the percentage change is quite consistent at around 15 to 20% change. On the other hand, the drag coefficient does not see a consistent change like the lift coefficient does. For example, the fluctuations increase gradually as the angle of attack increases, but once it hits 14-degree angle of attack, so this one around here, the fluctuations in the drag coefficient drop significantly. So for example, at an 8-degree angle of attack, the fluctuations in the drag coefficient are about 27%. So just this one here. And this depends on whether the airfoil is over a peak or the trough of the wave. Then if we go to a 14-degree angle of attack, this fluctuation is now about 32%, so it's increased by about 5%. But then at 18 degrees, this fluctuation is down to only 24%. So I think that this drop here after a 14-degree angle attack occurs because we're in the stalling phase of the wing and the stalling pattern. So this wing typically stalls from the trailing edge upwards. And if you were to just to time average everything out and not care about the fluctuations, and then compare the effects of the wavy ground effect on the ground effect when you just have a regular flat ground, you'd see that they have you'd see what they have in figure 8 here. So here they have the ground effect of this NACA 4412 over flat ground, which is this red line. Then they averaged out the ground effect over the wavy ground, which is the blue line. And quite amazingly, they all line up. Like the lift coefficient, the drag coefficient, and the moment coefficients are incredibly similar. There's only a tiny change. And this could very well be due to just the error in the CFD. I mean, with this particular CFD setup, I'd expect the accuracy to be about 2% perhaps, 3%. It's quite good, so I wouldn't expect it to be much better than that, but it would be around 2 to 3%, which is quite good anyway. So these errors that we are seeing between the flat ground and the wavy ground are probably going to be taken up by that error there. So we can pretty much conclude that putting the airfoil over a flat ground, flying over a flat ground compared to flying over a wavy ground, doesn't really change the efficiency of the airfoil over time. Sure, the wavy ground will change the efficiency depending on whether you're over a trough or a peak, but as you fly over time, you're going to be flying over thousands of peaks and troughs, thousands of complete wavelengths. That then averages out, which then results in the effects of the wavy ground to be negligible in the general efficiency of the aircraft. So that's quite amazing. I didn't expect that to be quite the case, because what this means is that the ground effect is fairly linear. So that means that in this particular case, with the wavy ground, with the trough, when you're like 15% of the chord away from the surface effectively, that means that the wavy effect is like 1/3 of that compared to when you're only over the peak, which is 5% away from the 5% of the chord away from the airfoil. There's a linear change in the lift, drag, and moment coefficients. What's also interesting is that all three of these coefficients linearly changed as well. So I would expect maybe one of them to be changed, but for all three of them to be changed linearly, that's quite impressive as well. That's quite unexpected. That means that flying over like an ocean surface doesn't really make much of a difference to the overall efficiency of the aircraft. Now, having said that, it is important to stress that this CFD setup in this study did not take into account any changes to the waves that the airfoil has when you fly over them, nor different sized waves. So often when you have waves going in like an ocean, for example, one wave will not be the same size or even shape as the preceding or proceeding wave. So they'll change over time. That's to be expected, but this is a preliminary investigation, and still these results are quite interesting and they're very useful. So those are the forces of the airfoil. Let's move on to the flow feature analysis to get a clear understanding of what's happening and why it's happening. So let me zoom out a little bit so you can see this figure completely. Here we go. So we have in figure 9, it says here the velocity contours of different moments at 4-degree angle tack. So when we are at a moment of 0, then 25% of the wavelength, 50% of the wavelength, and 75% of the wavelength through the wave. And I should mention that B, which is figure 9b, which corresponds to 25% of the period, so 25% of the wavelength, that corresponds to a trough. And figure 9d, which corresponds to a period of 0.75, that corresponds to a peak on the wave. And then the other two figures are between the peak and the trough, so like on the upslope or the downslope of the peak and trough / trough and peak regions. So from these figures, we have the velocity magnitudes around the airfoils, and it's a little difficult to see the changes, but a couple obvious ones include that the velocity under the airfoil greatly changes depending on whether the airfoil is over a trough or a peak. For example, in figure 9b, which corresponds to when the airfoil is over a trough, the airfoil, as expected, the velocity is fairly fast here. Then in figure 9d, when the airfoil is over a peak, the velocity under the airfoil is much slower. So we can see here it's bluer, whereas here it's much more green. And if we compare these airfoils to the lift and drag coefficients plotted in figure 6, we see that figure 9b corresponds to when the airfoil experiences a drop in the lift coefficient and a rise in the drag coefficient, whereas figure 9d, which is when the airfoil is over the peak of the wave, the lift coefficient increases and the drag coefficient drops. In addition to this change, in addition to the change in the velocity under the airfoil, the velocity above the airfoil changes too, albeit to a smaller extent. So we can see here that if we compare 9d to 9b, these velocity contours sort of change a little bit the area that it moves over, it encompasses. When the airfoil is over a trough, for example in 9b, the velocity above the airfoil is quite a bit higher than when the airfoil is over a peak of the wave. And this is an interesting phenomenon when you tie it into what is happening underneath the airfoil, and that is because in this particular situation, when the velocity drops, the pressure drops, and this is the basic Bernoulli equation that we all know and love. So we know that like the velocity and pressure are inversely coupled, and if you want to learn more about that, on our YouTube channel we have the Bernoulli equation explained in one of our aero fundamentals videos. So when we have the airfoil is over a peak and the velocity underneath the airfoil and above the airfoil drops, the pressure increases because of Bernoulli's equation. However, from figure 6, we know that at this point, the lift increases and the drag drops. That means that the increase in the pressure below the airfoil must be greater than the increase in the pressure above the airfoil in order for that to happen. So what I mean is, because we know the lift increases, if the pressure underneath the airfoil increased to the same extent as on top of the airfoil, or less, then we'd be getting a net equals like net zero or net reduction in the lift. But if we get a net increase in the lift, it means that the pressure underneath the airfoil must be greater than over the top, and that increase must be to a greater extent for that to happen. That's the only way that we can get that to happen. So that tells us a lot there. So I now mentioned that the drag coefficient over the airfoil over the wave's peak was lower than that when it was over the trough. And I think this has to do a lot with the rear portion of the airfoil, because if you look at figures 9b and d, you'll see that even though the velocity in figure 9d is lower for most of the airfoil's underside, so you can see here it's a lot more bluer compared to greener for 9b. When you get to the trailing edge of 9d, the velocity starts to increase quite a lot, and now it starts to be greater than for 9b. So I think that there's kind of a Venturi effect happening here, and that acceleration at the rear of the airfoil means that there is a faster moving flow flowing into the free stream flow and reducing the wake size potentially. So you can see that the wake size is a little bit smaller perhaps, and like not as green as for 9b. So I think that is maybe why the drag coefficient drops when the airfoil is over the peak of the wave compared to over the trough, or at least maybe one of the reasons. So let's move on now to not figure 11, we're going to go further to figure 12. Oh no, sorry, figure 11. Let me get this figure back up here. So figure 11 shows the pressure coefficients of the airfoil over different parts of the wave, and figure 11b shows this for when the airfoil is at a 4-degree angle of attack. The final thing that these researchers looked into was the effect of the ride height on the wave's ground effect. But before we get into that, we need to see that there are slight differences in the pressure distribution over the airfoil for all angles of attack that we have here. Now in figure 12, we have what I was mentioning earlier, which is the effect of the different ride heights over the airfoil. And we have it for 0-degree angle attack, which is figure 12, and 4-degree angle attack, which is figure 13. And interestingly, they only have the lift and moment coefficients. I don't know why they don't have the drag coefficients. That's beyond me. They maybe should have included that, but I don't know. Maybe they mimic the lift and drag coefficient, the lift and moment coefficients. So figure 13 shows the lift and moment coefficients for different ride heights and angle attack of 4 degrees. The ride heights change from 10% of the chord away from the ground to 100% of the chord away from the ground. And as expected from other ground effect research, which we did a podcast on quite a long time ago, as the ride height increases, the ground effect reduces. What's more, the waviness in the lift and moment coefficients introduced by the wavy ground also reduces. So we can see here, when we have a ride height of 100% of the chord of the airfoil, the waviness of the lift coefficient is almost negligible, like it changes almost nothing. So we can pretty much conclude that once you get like even one chord length away from the surface of the ocean, the waves don't really affect the airfoil very much. Now, I should stress that this is also for the wave sizes that they have here. If you had much bigger waves, then you might need to go further away from the ocean surface. But as we go quite close to the surface, so a 10% of the chord away from the ocean surface, the waviness of the waves affect the lift coefficient dramatically. So we can see that there's a fluctuation of like 10%. So the average lift coefficient is like 1, and this fluctuates between 0.9 and 1.05. So that's quite a big difference. Now, interestingly, the lift coefficient, the moment coefficient, is also affected by a similar extent. So when we go to a quite a far distance away from the ocean surface of 100% of the chord away, there's almost no effect of the waves on the moment coefficient. When we go quite close, 10% of the chord away from the ocean surface, there is quite a big difference. And another thing that we should mention is that we have pretty much the ground effect being shown right here. So for the lift coefficient, for example, when we are at a right height of 100% of the chord away from the ocean surface, the lift coefficient is about 0.77. And as I mentioned, this is pretty much stable here. As we go to a right height of 10% from the surface height, from the surface, the lift coefficient is about 0.98. So it's increased by about 0.2, so like about 25%, 30% of the original lift coefficient that we get when we are far away from the ocean surface. That's the ground effect happening right there, and it shows just how beneficial it can be for flying around. It definitely increases the efficiency of the lift production. So that's in a nutshell how the ground effect works, and the waves don't really have much of an effect when you average it out, as we saw earlier. So that brings us to the end of this podcast, and I think the most surprising thing, for me at least, was how if you average out the effects of the wavy ground on the lift, drag, and moment coefficients, as I'll get to here, let me go back up to this graph here. When you average these effects out, the results are almost identical to the results of the ground effect if the airfoil is over just a flat, regular ground. That indicates that there is a lot of linearity to the ground effect, which I wasn't quite expecting. And also it indicates that the waves, even though, for example, in the last podcast, when we had the lift and drag and moment coefficients plotted, we found that they weren't really sinusoidal. Even though they're not sinusoidal, they still somehow average out. So that's quite interesting as well. I don't know why that happens exactly. What that means is that the detrimental effects of the airfoil then be spread over a greater period, but those detrimental effects are smaller per unit time effectively than the beneficial effects, which are crammed into a much smaller period of time. So that's quite interesting, that linearity there, not just with the lift coefficient, but with like the spatial side of this in terms of how far away from the surface, but also the temporal side. There's linearity in both of these things, or at least maybe they might both cancel out the changes. So that's the end of this podcast. If you liked it, make sure to like it. If you want to see more like this, subscribe or follow if you're on Spotify or Google Play or whatever it is. And if you want to get better at CFD like this or theory like this, check out our courses in the link in the description. And if you want to make your experiments 2 to 4% more accurate, check out that Mr. Hawk. It's an instrument we make to make your experiments that much more accurate. And the reason why it does this is because the density of air changes by 2 to 4% every day. And that's on a regular day, not on like a special day when you have like a hurricane or something, but just a regular day where you come into work and it's a nice sunny day, and then you come back after lunch and you feel like having an afternoon siesta, but you still have to go back to work. The density of air has changed already by that much. And if you don't take that into account, your experiments will have that error into it to begin with. And what's more, even when you first start your experiments, you don't know what the density of air is. So if you assume it to be 1.2 kilograms per meter cubed or 1.225 or whatever it is, then that's going to be wrong because the density of air in your wind tunnel is not that. So that introduces a great error into your results. And then if you were to come back tomorrow or the next week, or the next month, the next season, those changes will be even greater. So you want to make sure to get rid of those by using an instrument that accurately measures the density of air. And the Atmosphere Hawk does that for you. What's more, we're talking about CFD here. And for example, with this research, they needed to use experimental data to validate the CFD like most people do. And if you're using your experimental data, which you don't know the density of air to, and then you try to use that to validate your CFD, there's obviously going to be a mismatch there because the CFD density that you use is very different to your experiments, and you don't even know it. So that's going to mean that your CFD is going to be erroneous without you even knowing it either. So that Atmosphere Hawk gets rid of that error for you. It's really, I would say, one of like the top 3 most important instruments you need in your wind tunnel, including a pitot-static tube. It's like that important, which most people don't have for some reason. So you can find that in the link in the description below. And I'll see you next video. Peace out, amigos.